So good evening, everyone. Today we are going to start the seventh week of fluid flow operations live sessions. So first we'll discuss the same way we'll discuss the lecture notes in details, and we'll go through some conceptions, some derivations, and we'll again then solve the mm, we'll then solve the assignment problems and some other mathematical problems. Okay, so let's start the session. I'm sharing a screen. Hope it will be visible. I think my screen is visible. Yeah. So in this lecture, Sav has mostly talk about the open channel flow, right? So open channel flow you have already seen, like it is in our daily life. It is nothing but the like the drain where the fluid flows, like where the water flows through the into the into the river or into the sea. So all these are examples of open channel flow, right? So they have some depth. Somewhere you can see there are a turbulent flow. Somewhere there is a kind of mixing, very fast velocity will be seen somewhere. Then you can think about the dams, right? These are also a very good example of open channel flow. You can see how the dam flows, how the water is stored first and then it has been released, and that is also based on the open channel flow concept. So we will study that. So yeah, this is a kind of example. So here also you can see an open channel example. So see all the river, all the kind of drains and all the type of natural flow you find in our surroundings. All these are open channel flow, but these are all in microscopic scale. We want to mimic this in macroscopic scale, sorry. So we can also mimic these things in our microchannel flow. So we can make a open microchannel flow which has suppose only 300 diameter. Okay, 300 micrometer diameter. Okay, so that is the microchannel flow. So these things are have been studying in the laboratory scale for years. But this is the macro scale, like this. So this is the channel, and this is the depth of the channel. This is the area, and this is the external part is the perimeter. And here the force balance is happening. Okay. So how the force balance is happening? It is happening. So if the cross-sectional area of the open channel is A and the length is length of the weighted perimeter is S, right? And the mean value of the shear stress is tau 0. So what can we say? We can say, if we consider, we can balance this, right? We can balance. This is the sine theta component of the flow which is acting in this direction, and this is equal to the stress uh, like tangential force term, right? This is balanced with the tau 0 SS. So here theta is very small, so we can consider tan theta is equivalent to sine theta, and we can define it as I. And this is how this expression is coming. So here you have, only last class you have studied about the friction factor coefficient, right? So friction factor is the shear stress by rho v square by 2, right? So if you compare these two terms, if you do an equilibrium between equality between these two terms, you will get the velocity of this term. And this c is this value root over 2g by f, and this is called the Chase's formula, and it has been varied depending upon the different experiments, and throughout the years different scientists have defined this c value with their own experimental value. Depending on their own experiment, they have changed it, like little bit modified, and they have found some empirical equations. Okay. So these are the values of alpha and A based on the wall surface tension. So it can be varied for how you can see that how much different types of channels are present, open channels are present in reality. Okay, so based on the channel shape and all, this N value and alpha value has been varied. So this is the Manning equation. So from here we can calculate the discharge of a water channel. Okay, so discharge, you know that Q equals to V into A, right? So here you have already found the expression of V, and you can calculate it from here. So now next, this is the equation part. So this is the circular, like flow in a water flow in a circular channel. So then the equation will vary like this. So this is just a mathematical jugglery is happening here, nothing else. A very simple algebra has been done. See, these are the expressions. So this is the V by V flow velocity and the discharge ratio. Okay. Whenever the maximum capacity of the channel is flowing. So this is the for the water flow in a rectangular channel. Last one is the circular channel flow. This one is the rectangular channel flow. So you can see that height by this width ratio is half. Here also they have calculated using this also you can calculate the velocity and the flow discharge, right? Okay, so this is done here only. Next one is about the equation of energy. So equation of energy, if somebody tells you only remembers the Bernoulli's equation of energy. So here you have already seen that this is the kinetic head, this is the pressure head, this is the static head, right? And this is the datum level distance. So you can see that how difference distance and how the total head has been calculated. So in the last class we have calculated the total heads, and how first we have calculated the kinetic energy portion v square by 2g, then we have calculated the pressure difference after putting it in Bernoulli's equation. Equation we have calculated the pressure difference, and from there we have got the pressure head. Then we have got the static head, or sometimes it was already given, right? And here is the datum level distance. So this is how you can calculate the total head, if you remember the last class. And if you don't, please go back to the previous lecture. Last week I have taught, and it has been online in the YouTube. So this H is called the depth of water channel, right? So this rho P, this pressure head plus static head is like collectively called the depth of water channel, right? So this is the, now this H equals to P by rho G plus Z. I hope you are understanding, but again, okay, I'm drawing so that it will be much more easier for you to understand. So suppose a channel is flowing, a channel is there, it has some, like, this is the downstream flow is happening. Okay, so this is the distance from the datum level or reference level, you can say. So this is the datum or reference level. Okay, so this is the Z0. This per portion, the channel, this is the depth of the channel. This is Z0, this is the depth of the channel. This is the depth of the channel, which has been defined by H, and which is nothing but the pressure head and the static head, right? Right? And there is another portion, that is the kinetic head, that is the V square by 2G. Kinetic head. So this is the pressure head, which is the static head, right? So now what is happening? So it is written that the total head relative to the channel bottom is called the specific energy E, and which expresses the energy per unit weight. And if the cross-sectional area of the open channel is A and the discharge Q, then this relation happens. So when we consider the total, this total area, and that means the total energy head, like total energy head. Okay, so it is nothing, it's in like its unit is energy per weight. Okay, so total, when we are considering the whole thing, this is the total energy head E, or ET you can write. And if we are not considering the datum level part, that means now we have shifted our base to this level. Now we have shifted our datum to this level. So this, only this portion we are calculating. This is the specific energy head. Okay, this is the specific energy head E, which they are talking about. This is H plus Q square by, what is written? Q square by 2G square. So we have seen that. So first, the total head, where that means ET considers all this term, right? ET considers all this term of Z0 plus H plus V square by 2G, and specific, and this only portion this only portion is the your specific energy part, that is the E. And how q square by square? So you already know that q equals to, that means this charge is area into velocity, that means v equals to q by a. So if you substitute the expression of v here, you will get this h plus q square by 2g a square, right? Easy, very easy. So this is how the specific energy expression is coming. Now see what is happening. So now we are getting, now what is the specific energy? So if you write again, so we are mostly interested about the specific energy calculation, okay, because this is very important. You will get to know why. So total energy, where the distance of the water channel from the reference level is considered, but in case of specific energy, this reference has been omitted. Okay, so now we have got the expression like h plus not v square by 2g, we write the expression q square by 2g a square, right? So h is what? H is considering your static head plus kinetic head, which collectively you can call it as potential energy. So basically this H is you're talking about your potential specific energy, and this portion is the kinetic potential energy, right? Because it has some velocity term associated with it. So you can remember it as EP and EK. Okay. So now there is a graph, right? What it has been saying. So it is a graph of energy. This is called the energy curve. Okay. So this talks about, so this is now what I am going to draw is the energy curve. So what is energy curve? This is nothing but the variation of energy with depth of water channel. Why? Because you can see now that suppose this is a graph. This is our graph. So here we are calculating E energy. In the x-axis there is specific energy. When I am talking about energy, you always remember that I am talking about specific energy, because we are already defined that E is nothing but the specific energy. We are nowhere talking about the total energy. Okay, I hope you will get it. So this is the height. That means not height, you can call it as the depth of the channel. So now see, so we are plotting this EP and ET. So as you can see, it is just proportional. EP, potential energy, just proportional to the specific energy term. So what it will have? So it will have just a straight line. So this straight line represents your potential energy, right? And there is second curve, right? You can see here, right? So this is your parabolic curve. So here you can see, okay, so this is your EK curve, okay, that is the kinetic energy, specific energy curve. So together, if you combine these two, because specific energy is represented by both of them, so you will get a curve like this, okay. So this is your specific energy curve. This is your final E curve, okay. So what you can understand that your potential energy curve is just proportional to, is just a straight line, and it has a 45-degree angle. So if I write, so EP curve is straight line with a 45-degree angle, right? And EK curve is parabolic, right? So this like some kind of MCQ can come. Okay, so like how the potential energy curve and the kinetic energy curve varies. Okay, so combining these two, you will get a actual specific energy curve. What else is there in this curve? So now you can see here. So for the specific energy curve, this is the lowest point. You can see, right? This is the lowest point. So now if you mark the y-axis and as well as the x-axis of this curve, this point is called the lowest critical specific energy point. So you can see here, this is the critical specific energy point, or better if you write it here. So in the x-axis it will be EC and in the y-axis it will be HC. So what is EC and HC? EC is the critical specific energy and HC is the critical depth, right? Because this is the lowest point of this specific energy curve. Beyond that, if you go this side or if you go down, you will get always greater value from this critical value. So what you will know that in real case you cannot, in reality or in real world, you cannot go below this point, like whatever energy curve portion is there, because as you can see, this line is already cutting through the EP curve and EK curve, right? Potential curve and the kinetic curve. So beyond, like below this point, whatever energy is there, whatever specific energy is there, you cannot achieve that kind of energy in reality. Okay, ideally you can achieve, obviously, but for a given system, for a given water channel, for a given shape of water channel, if the where the this minimum point is cutting through the EK and EP curve, below this point you cannot achieve this energy in real sense. Okay, so above that you have to calculate, always you will get always the above, right? So this is your minimum point, like critical specific energy point. This is the critical depth. So as well as the definition becomes that what is critical depth? Critical depth is nothing but where the specific energy is minimum, right? You can see here the specific energy is minimum. So I can write again. So critical depth, definition of critical depth, if somebody asks, so it is the point at which the specific energy is minimum. Okay, so this is the definition of critical path. Now what else is there? So you can see. So what it is telling, that beyond this point, if I go back to the curve again, so you can see that beyond this point, like, okay, in the top portion, there will be a tranquil flow. That means that will basically a calm flow or laminar flow, in that sense you can tell. It is a tranquil flow, and below this point, that means if the height of the water channel or depth of the water channel is below the critical point, okay, that will be a rapid flow or turbulent kind of flow. So we'll define this term again. How? We'll see. So let's go back to the lecture first. So we have understood this curve, right? Next, what is happening? So now, as you can see, that we have already got it, right? This is the, so what it is said that at the minimum point, so at the EC, at the HC, the E is minimum, right? We have just seen. We have just seen. So now how can you calculate this expression? That means at HC, so if I write, so at HC, specific energy is minimum. That means dE or d by dH will be 0, right? Now I can differentiate it. What is the expression of E? So E is H plus Q square by 2GA square. Now if we differentiate this, what will come? So dE by dH, we are differentiating it, okay? So first term will be 1 plus Q square by 2G will be constant. It is known that A is the area of the channel, right? A is the area of the channel. So it is B is the, suppose B is the width and H is the height. So A equals to BH. And if the discharge per unit width is given by Q, then capital Q is Q into B, right? And now we will put this value here. So what E will come, specific energy will come H plus Q squared B square by 2G B square H square, right? So now B square will be cancelled out. So what is the expression of E? E is H plus Q square by 2G H square. Now we will get the derivation. So what it is telling? So if you do the derivation, so what it will come? So the expression of E, let me write again. Expression of E is H plus small q square by 2GH square, right? Check it. Yeah. So now we are finding the critical depth. So dE dH equals to 0. So it is, now we are differentiating. So it will be 1 plus q square by small q square by 2g will be your constant. So it will be h to the power minus 2. But basically means minus 2 to 1 by h cube equals to 0. So now what is coming? 1 minus q square, 2 will be cancelled out, gh cube equals to 0. So 1 equals to q square gh cube, right? So it is coming as like expression of h cube. If you find h cube equals to q square by g, right? So our expression is matching with this. Yeah. So now, so what we know, this is minimum at HC, right? So we will write as HC, or if we take cube root of this this expression, so it will be HC q square by g to the power 1/3. So this is the expression of critical depth. Now going back to the lecture again. Okay, so here we have found the expression of critical depth, and similarly it is the from critical depth we have, if you put the value of Hc, if we put the value of Hc, we will found the critical specific energy. So EC will be Hc plus Q square by 2G Hc square, right? So what will it be? Hc plus Q square by 2G Hc expression we have got, right? It is Q square by G to the power 1/3. That means 2/3. So it will be Q square by G to the power 2/3 because it is square. So now if you calculate what it will come, is it coming? So if we now want to do this, what is the value of Q coming? So Q has, so from the previous expression also you can write. So here in this case what you are getting, you can apply that, right? You are getting that from this previous expression of the, like, not the last line, from the previous line you are getting that q square equals to gh cube, right? So in terms of, in this application we can, if we want to apply, so E will be hc plus q square term will be hc cube by 2ghc square, right? Forget about this line for now. You can solve it from here also, but if you want to more simplified version, this is a more simplified version. So directly from here you can come here, right? Using the previous expression. So now what it is? So E is hc plus, you can see one is left. So hc plus 1 hc by 2 is left. So this is nothing but 1.5. Like, so this is the 1.5 hc equals to ec equals to 1.5 into hc. So it is what this is written here, that specific energy in the critical situation is 1.5 times the critical water depth, right? Now what is coming next? So they are doing some problem, we will be doing also. So critical velocity also you can found now. So it is corresponding to the small vc, right? This is the capital Q by hc. If you put the value of hc, you will get the root over gc term. I'm not doing it, you can do it on your own, because these things are very important to remember for your exam to solve the problems, mathematical problems. Okay. Now this is an equation. So if you again want me to do the expression of critical velocity, so I can do, no problem in that. So what it is? So velocity was q by a, right? So q, you know, q into b by a is b into h. So it is nothing but q by h. So critical velocity means vc equals to q by hc. right? So we have now the expression of Hc, right? So it is Q by, like, what was the expression? Q square by G to the power 1/3. Q square by G to the power 1/3, right? So what it is that? Or it is not taking the expression of, it is finding this in terms of Hc only. So forget about this step. So from the previous step, we have seen that Q square equals to GHQ, right? So Q will be GHC cube root under, and bottom there is Hc. That means, so now G is to the power half, Hc is 3 by 2, bottom it is 1. So 3 by 2 minus 1 basically. So 3 by 2 minus 1 means it is 1 by 2. Right? So it will be G to the power half, Hc to the power half, so it is GHc. So Vc is GHc. So this is the expression of critical velocity. Okay. I am doing this because you will need to solve the problems. So now comes the subcritical flow and supercritical flow. Okay, so in the curve we have seen, so if you remember the curve, or let me draw it again. So in the curve, what was that? It is the H, pardon, my drawing is not good. It has to be very straight. So it is the specific energy curve E versus H, right? So I'm not drawing the potential part or kinetic part. It has been done already. So now this is the your specific energy curve. This is the minimum point, right? This is a critical point. This is your EC. This is your HC. Now, when this thing will be, like, suppose there is a distance here. We are calculating something at this point. So this distance is H less than HC, right? And there is another distance, the top. So this distance is H greater than HC, right? So beyond the critical point, we have seen that this is the tranquil part and this is the rapid part. So it is what it is written here. If the flow depth is deeper or shallower than HC, then flow behavior is different. So when the water is deeper than the HC, right? That means water depth H is greater than the HC, the velocity is smaller. That is the tranquil part. That means the flow is tranquil, then the velocity is smaller than the traveling velocity of the long wave. This type of flow is called the tranquil flow or subcritical flow. This is what I said just now. So this is your tranquil part or subcritical part. And when H, the water depth is less than the critical depth, so that is a rapid part or supercritical part. Okay. So now it is written that when the water depth is shallower than HC, the velocity is larger than the traveling velocity of the long wave. This type of flow is called rapid or supercritical flow. I hope you have understood now. What are these? You have to be clear in your head while drawing the curve. If you know the curve very well, you can automatically predict. You don't need to remember what is sub or super and give a pressure on your head. You just draw the curve and you can automatically understand how this, when the H is below, HC, this is the supercritical portion, and when the H is above HC, it is the subcritical portion. Okay. Okay. So we have seen that in case of constant water bath, E and H ratio is 1.5. Okay. For a rectangular channel. So there is some problem here regarding that. So now comes the hydraulic jump. So what is hydraulic jump? So it is I will show you some videos about like normal YouTube videos you can yourself also find, but I will show you that what are these different terms called. Let me finish first. So it is a phenomenon of flow when liquid at high velocity discharges into a zone of lower velocity. A rather abrupt rise occurs in the liquid surface. Right? So here in this portion you have seen earlier that this is the your subcritical portion. Now flow is going to this portion, and suddenly there is a chaotic motion is creating, and this chaotic motion will make the flow unstable, and it will suddenly wants to come back. It will create a backflow or back pressure towards the lower velocity zone, that is the subcritical zone, and that is called the hydraulic jump. Okay, rapid flow is unstable, and if decelerated, it suddenly shifts to subcritical flow, right? Suppose a flow is happening. If you want a figure, so suppose there in the dam, sorry, not like this. It has to be like a slope kind of thing. A dam is there. Suppose a dam is made on the path of a river. So fluid is coming very slowly and it is going to this direction, and it is going from subcritical. This is the subcritical zone to supercritical zone, and when it is jumping, it is the depth becomes less than the critical depth, so it starts as a chaotic mixing, chaotic motion. Okay, you can see chaotic motion, and suddenly it will again create a backflow kind of thing. A back it some and after some time it will experience a backflow, and it will create a it wants to go back to the subcritical zone, and it creates a hydraulic jump here. So this is your hydraulic jump here. Okay. So if you see the here, you can understand that flow is coming. So what is saying, when the inclination of a dam bottom is steep, the flow is rapid. When the inclination becomes gentle downstream, the flow is unable to maintain rapid flow and suddenly shifts to the subcritical flow, right? Like if the slope of the dam is very steep, the subcritical flow will not happen. Like the jump will not, hydraulic jump will not happen. It will, because it will always be rapid. But suddenly, if the downstream slope is very gentle and the flow is unable to maintain the rapid flow and suddenly shift to the subcritical flow, and it creates a jump. So here you can see that from the subcritical zone it is coming to the drawing I have made, it is coming to the supercritical zone, but after some time suddenly it cannot maintain this supercritical flow, and it faces a back pressure, and it wants to convert to the subcritical flow, and there is a jump here. So this is the jump here that is happening. It is represented by these terms. Okay. So wave velocity, so what is the wave velocity at that time? So we have seen that the velocity or minimum velocity or critical velocity is represented by root under gh. So wave velocity will also be root under gh. So this is also defined by the subcritical flow, Froude number, which is in dimensionless number. So Froude number is the FR number is equals to, it has two expression. I will come to that, like inertial force by gravitational force. Okay, so inertial flow is mass into acceleration, m into n. Gravitational force is mass into gravity, mass into gravitational acceleration, that is g, right? Now mm will be cancelled out, so this is nothing but the a by g. What is a? A is velocity per time, right? And by g, so it is v by tg. And what is t? How can we calculate the t? T is your like velocity per depth, right? Sorry, I have said wrong. It is the depth per velocity, right? It is the v. How time is defined? Time is defined as depth. Suppose d is the depth, or you can say h is the depth here. H by v into g. So what it is coming? V square by hg. This is your Froude number expression. Okay. And right now we have seen that v is critical velocity. V has also an expression of root under, so v square by hg is also, v square means so this is also, we have seen that like vc, we have seen that root under gh, or you can say wave velocity, not vc, or you can see vc GHC, right? From there you can say that it is the Vc square. So it is the ratio of traveling velocity of the wave, ratio of flow velocity to the traveling velocity, right? So it can be the ratio of flow velocity by traveling velocity. Okay, you can see here, right? So when this V equals to Vc, right? When Fr equals to 1, that means V equals to Vc. So that is your critical flow. When Fr less than 1, that means flow velocity is less than the critical velocity. So that is your subcritical zone, subcritical flow. And when Froude number is greater than 1, that means V is like flow velocity is greater than the traveling velocity. It is coming as supercritical zone, the rapid zone, rapid flow zone, right? You can see the Froude number of the subcritical flow is less than 1. Yeah. So the subcritical flow and rapid flow in a water channel correspond to the subsonic flow also. And supersonic flow is corresponds to the uh, supercritical flow. And when we are calling it subsonic or supersonic, when when these things are, when the fluid is a compressible gas, right? Very simple. When this is, we are talking about only fluid. So gas is also one type of fluid. So when we are talking about fluid or liquid, so that is the subcritical and supercritical. And when it comes to compressible gas, it is the subsonic and supersonic. Okay, I hope you have got it. So you can see analogy between the hydraulic jump and the shock wave. So for the flow of gas in a convergent or divergent nozzle, supersonic flow which has gone through the nozzle stays supersonic if the back pressure is low, right? And if the back pressure is high, what I was talking about earlier, the flow suddenly shifts to the subsonic zone, and that comes with a shock wave. So in case of fluid, it is called the hydraulic jump, and in case of liquid, it is called the hydraulic jump. Okay. Hydraulic jump is required to prevent the erosion of the channel. Okay. So now we'll see videos of these very interesting videos. Then I will do some problems on that. Here, see. So this is, you can imagine that this is our river dam where the river is expanding, and suddenly there is a depth where the height is like depth is below the critical depth, and the water is flowing through this portion, and suddenly there is a chaotic motion. This is called the supercritical zone. And if that is going on for a long time, and suddenly this cannot maintain, and suddenly wants to go back to the subcritical portion, it is having a back pressure, and it will be creating a hydraulic jump. You can see in the video. See how the hydraulic jump has been created. Why the hydraulic jump has been created here? Because the downstream bottom portion is similar. Like there is not very sharp steep. It is very less the downstream is very gentle. That is why this happens. So here it is written. So less than is supercritical, equal is this one. So how a Froude number you have seen. Here you can see. So now the hydraulic jump is happening in this portion. The jump or standing wave formed when the depth of flow of water changes from supercritical to subcritical state. Here you can see. So there is one thing I need to mention here. I mean, mention for I forgot to mention. So this is the Not only inertial force or gravitational force, it is the root under inertial force and root under gravitational force. Okay, so these are all under root. Sorry for the mistake. Please correct in your notes. It is coming like this. So this is all under root. So it is root under V by root under T into G. Then T can be represented at H by V. So it is nothing but V square under root G, that is, it is nothing but V by root under Hg. So there will be no square term. So it is exactly the ratio of flow velocity by traveling velocity. Okay. Now it will be much more easier. Sorry for the mistake. I have corrected it. Please you correct yourself. So what I was showing the video, right? Yes. So this is the hydraulic jump here. It is because it is trying to coming back from supercritical to subcritical state, right? So subcritical depth flow is happening. Subcritical depth or subcritical flow, if you do something, if you put objection there, it will have nothing effect. So here the objection is there. See. So subcritical flow, this is the stone or broom. This is the supercritical flow, stone or broom. So this will go, the flow wave will be continuously moving. Okay. I hope you have, I already have cleared. I have shown you a video. I think it will be much more clear. Okay. Now going back to the lecture to solve the assignment questions and some more interesting questions. Okay. Let's do. In a water channel, the flow behavior is turbulent, laminar, transition, or ideal. So, you know that in the open channel kind of thing, the because the surface is free here, suppose it is water, so it is free surface. It has free surface of water, so it will always have high flow rates and larger dimension. So RE, in case of RE, rho V D by mu, so D is very high because its depth will be very high. So it will automatically will reach in the turbulent zone. So it is always the turbulent. In open channel, it is water flow is turbulent. Next. In the water channel, the mean velocity u is at what depth? So in the lecture notes, it is given that in the water channel, the mean velocity is the mean velocity u is at 50 to 70% depth because of the friction and bed resistance. Next, in order to maximize the flow rate Q, the depth of the water channel should be what of its width? Think and tell me. So flow rate is Q equals to VA, right? A Q equals to VBH. B is width, H is height. So in order to maximize the flow rate, so this depth of the channel should be half of the width. So this B width is there and half H should be B by 2, right? Then you can get the maximized flow rate Q. So this is 1/2. Question 4. Water channels have the flowing characteristics. Which on the following is true? Water channels have the channel where a stream of water flows with a free surface exposed to the open air. It is true. Water channels have large hydraulic mean depths. It is also true. In a water channel, the Reynolds number is large and the flow is turbulent. It is also true. So the answer will be option B. Next question. A rectangular channel is having a depth of 2 meters. Sorry. Yeah. And with 3 meters. Bed slope of 1 in 50. The value of Manning's roughness coefficient is 0.05. Estimate the discharge through the channel. You can tell me the answer. I'm waiting. So now you can calculate first the area. So Manning equation, if you remember, this Manning equation, if you remember, it is Q equals to 1 by N A M 2 to the power 3 m to the power 2 by 3 and I to the power half, right? So now you have got everything. So area, you know, area is given, 1 by N is also given, it is 0.05, right? A is 2 into 3, that is the depth. You know what is M? M is A by P, right? So M is the area by perimeter. So area is 2 into 3 and perimeter is B plus 2y because there is two sides. B plus 2y means the like it is, if it is B and y, if you can write in this way also. So it is B into H. It is B into H. Y means H only. So it is 3 into 2 by 3 plus 2 into 2. So it is 6 by 7. Right? So it is 6 by 7 means what? You have to calculate. 6 by 7 is 0.857. So it is 0.857. So it is 0.857 to the power 2/3. And I is given as, slope is given as 1 in fifth. So 1 by 500 to the power half. Now calculate and tell me. So it is coming as 4.842 meter cube per second. So it is close to this, option C. Next, the relation between the hydraulic mean depth and hydraulic radius of a rectangular water channel. So in a rectangular water channel, hydraulic mean depth H is the hydraulic radius. So it is larger. The depth is always larger in a rectangular channel. Okay, so suppose this is a rectangular channel. So it is the radius R and depth H. So H is always greater than R here. Option B. Next, consider a fully charged flow. Which of the following shape will have a shortest length of the weighted parameter for the given area? So it will always be the circle, because circle perimeter will give the shortest length. Okay, so it is option D. Excuse me. Next, consider a section is selected in such a way that the weighted perimeter is minimized. For such a case, the discharge and mean flow velocity will be what? So minimizing perimeter, right? Minimizing perimeter will increase the area, will help in increasing the area, and the it will reduce the frictional resistance. Okay, that means the flow discharge velocity and mean flow velocity will be high. So maximum discharge and flow velocity. Okay, so it is maximum. Next, at large Reynolds number, the friction coefficient becomes constant. It is true or false? So you have seen in the class the Morse chart, right? So if you remember the Morse chart, so it is going like this, right? It is for RE, it is RE versus F. And this portion is for laminar flow and this portion is for turbulent flow. And you have seen that in the high velocity region, that means the higher Reynolds number, the friction coefficient F is not anymore dependent on the Reynolds number, so it becomes constant. You can see here the graph, you can see, right? It is only dependent on the surface roughness, so it is true. Select the correct Manning equation for discharge, where Q is the discharge of fluid, N is the Gockler-Manning coefficient, M is the hydraulic mean depth, and I is the inclination. So it has to be m to the power 2 by 3 and I to the power 1 by 2. So it is the option D only. We have just solved an equation depending on Manning equation. The specific energy in the critical situation is what times the critical water depth. So we have defined it, or we have done the derivation of it. So EC equals to 1.5 of HC. It is option D. Next, a low value of Froude number means these are large in comparison with this. So what we have seen, Fr is the root under inertial forces by gravity forces, right? So if it is very low value of Froude number means gravity force is larger than the inertial force. So in case of A, it will be option D. It will be gravity forces are large in comparison with inertial forces, option D. Next, in the case of an open channel, the total head relative to the channel bottom is called the specific energy E. If the cross-sectional area of the open channel is A and the discharge is Q, then which one is correct? So we have done this calculation, it is option A. E specific energy is H equals to H plus kinetic head. So kinetic head is the V square by 2G, and from V square by 2G, like EP plus EK, we have sent potential head plus kinetic head. It is the V square by 2G and V equals to QA. So it is nothing but the Q square by 2G A square, right? Next, for the constant discharge, which one of the following terms will be 0 to achieve the critical point for minimum energy? So it will always be, so we have seen this definition also we have done. So it is dE dH equals to 0 at HC, at critical depth. Next, find the critical water depth and the critical velocity when 12 meter cube per second of water is flowing in an open channel with a rectangular section of 4 meter wide. Okay. So it is asked for critical depth. So critical depth, we have know the expression. So HC equals to, oh, I might have forgotten the expression. So let me just check. and go back. That is why I have done the expression q square by g to the power 1/3, right? Q square by g to the power 1/3. Sorry, not this 1/3, it is whole 1/3, right? And what is q? Q we have known earlier that capital Q equals to Q into width. So Q will be 12 by 4, that is 3 meter square. It is meter cube per second. This is meter. So it is meter square per second, right? So now HC will be 3 square, that is 9 by 9.81 to the power 1/3. So it is coming as 0. It is coming as 0.971 meter. This value is not given, I don't know, but it has asked to find. Again, we have to find the critical velocity Vc. Vc expression was G into Hc. So now tell me what is the value. So this is coming as 3.087 meter per second. So it is close to I don't know, there might be some problem with the answer script. Not sure I am. Okay, so I'm not marking anything. Next question. When the water depth is shallower than the critical flow depth, the velocity is larger than the long wave traveling velocity. The type of flow is called what? So we have done it multiple times. We have seen video when the depth, water depth H is less than Hc. So it is the traveling velocity is larger than the fluid flow velocity. So it is the supercritical flow. Option B. Next. In general, the rapid flow showcases the unstable nature, and if decelerated, it suddenly shifts to what? So in general, rapid flow showcases an unstable nature. If decelerated, if suddenly suddenly shifts to subcritical flow. That is called the hydraulic jump. Option A. The Froude number for the supercritical flow is given as greater than 1. So Fr is greater than 1. That means Fr is the traveling velocity by the fluid flow velocity or critical velocity. So V is greater than Vc. So it is option C. This is the supercritical flow condition. Here you can find. Which of the following option fulfill the condition for subsonic and supersonic flow? The flow velocity is smaller than the wave. Subsonic and supersonic flow. The flow velocity is smaller than the wave velocity. Froude number of a rapid flow is larger than 1, the flow velocity is larger than the wave velocity. So for subsonic flow, this is option A. For supersonic flow, this is option C. Okay. This one is subsonic and this one is supersonic. Next, when a hydraulic jump is brought about, energy is collected by it. Thus, erosion of the channel bottom can be avoided. Whether the statement is true or false. This is true. Sorry, I made a mistake. Energy is not collected by it. Energy is dissipated by it. Hydraulic jump is brought because to prevent the erosion in the channel, and that is why energy is dissipated. So very careful about the terms. So it is false. Okay. Next. For a constant cross-sectional area and inclination, what conditions must be met to achieve maximum discharge and velocity in an open channel? The hydraulic mean depth must be minimized. The weighted perimeter must be minimized. The flow must be changed from subcritical to supercritical. The inclination angle theta must be maximized. So you have seen this, right? So it is the weighted parameter for achieve maximum discharge and velocity in an open channel. The hydraulic mean depth must be minimized. It is option A. Next, in the Ganguillet-Cotter and Basin equations, the flow velocity coefficient C is primarily a function of only the fluid density and gravity. The Reynolds number and friction factor, hydraulic mean depth M, inclination I, and surface roughness constant, the ratio of water depth to channel width. Let's go back to the lecture. In the previous question also, it will be the weighted perimeter must be minimized. So it will come like that, the the depth will be half of the channel depth will be half of channel width. Okay. So it is the weighted perimeter must be minimized. The next question, the Gutra basin equation we are going. This is the Manning equation. Here comes the you can see, right? M, I and N. So this N is the N is varying. It is depending on the surface roughness. So it will depend on this option C. Hydraulic mean depth M, inclination I and surface roughness constant. Third one, which dimensionless number is used to represent the flow velocity to the traveling velocity of a long wave? So it is the Froude number. Next, hydraulic jump typically occurs when flow shifts from subcritical to supercritical. Liquid at high velocity discharges into a zone of lower velocity, causing an abrupt rise in the surface. The channel bottom becomes extremely steep. The specific energy is exactly 1 times the water depth. So it is option B. Liquid at high velocity discharges into a zone of lower velocity. So it will be opposite. Supercritical to subcritical. Okay. Next. Now comes the mathematical questions. So you are designing a rectangular open channel to maximize flow velocity and discharge for a given cross-sectional area. What should be the relationship between the depth and the channel width? So this is what we are doing in the MCQ. So now we can prove it. So in the perimeter of the rectangle channel P is width plus 2 into height, right? And also we know the cross sectional area is A into BH, right? So we can now substitute B in the perimeter like AH. So perimeter will be A by H plus 2H. So now perimeter should be minimized, we know, right? So here for getting maximum low velocity and discharge, perimeter should be minimized. So dP dH will be 0, right? So it will be minus A by H square plus 2 equals to 0. So it will be A equals to 2H square, right? A will be 2H square. So now we know B, A equals to BH. So BH will be 2H square. So B will be 2H, or H will be like depth will be 1/2 of the width. Okay, so this is the relation. Next, water flows In a rectangular open channel that is 4 meters wide with a discharge rate, this find the critical water depth and the minimum specific energy EC. So we have known the critical depth is Q square by G 2 by 3. If you put all the values, it will come as, if you put the value, I am not putting the values, okay, 0. Or I can put like Q, we know that Q equals to capital Q by B, so it is nothing but 12 by 3, 12 by 4, sorry. So it is 3 square 9 by 9.81 to the power 2 by 2. It is coming as this meter, 0.97 meter. And EC is the minimum specific energy, we know, 1.5 HC. So it is coming as 1.455 meter. Okay, sorry, meter, not meter. Yeah, it is head, energy head. Yeah, it is meter, sorry. So in the same meter wide channel of the problem 2, that is the previous problem, the actual water depth is measured at 1.5 meter. Is the flow subcritical or supercritical? So actual depth is 1.5 meter, critical depth is 0.97 meter. So H is greater than HC, so that is your subcritical or tranquil, tranquil flow. Next, a circular storm drain has an inner radius R. If the water surface subtends an angle theta at the center, calculate the cross-sectional area A and the hydraulic mean depth. Think and tell me. So it is coming for a circular storm drain. So circular storm drain equation we have seen here. See, this is the circular channel, right? So cross-sectional area equation is given by, we have to see it because we have not remembered the expression. Where was it? Yeah, it is r square theta minus sine theta by 2. A cross-sectional area A is r square theta minus sine theta by 2. So theta we know, theta is in 120 degree, which is 2 pi by 3 radian obviously. So it will be 1 into theta value is in radian. Theta value should be in radian. So it is 2.093 radian. 2.093 radian minus sine 120, that is 0.866 by 2. So it is coming as 0.613. Area is 0.613 meter square. And the hydraulic depth. So the hydraulic depth is also given. Hydraulic mean depth formula is also given. R by 2 1 minus sine theta by theta. So mean hydraulic depth M is R by 2 1 sine theta by theta. So putting all the values, I am not putting again. So it is 0.293 meter. 0.293 meter. Okay, this is the answer. Next, using the results, find the discharge Q in the channel is made of non-finished concrete, that is N and I are given. So using Manning equation, we can found this like Q equals to 1 by N A M to the power 2 by 3 I to the power half. So N is given 1 by 0.015. A have calculated as 0.613 or 4, whatever it is. We are calculating 6.3 because we have got 6.3. 0.293 to the power 2/3 into 0.001 to the power 1/2. So how much is it coming? It is coming as 0.57 meter cube per second. Okay, next. A rectangular channel carries a flow with a specific energy 3 meter. Under critical flow conditions, what is the maximum possible discharge per unit width that is channel can handle? So we know that in case of critical specific energy is EC equals to 1.5 into HC. So now HC will be 3 by 1.5, that is nothing but 2 meter critical depth. So what is the maximum possible discharge per unit? So we have to calculate it from this. HC equals to Q square by g to the power 1/3. So hc cube into g will be q square, right? So q square is coming as 2 cube, that is 8 into 9.81, and under root of it. So this is 78.48, and q will be root under this 8.858. 8.858 discharge per unit weight, that is meter square per second. Okay. Next, water flows at a high velocity with a depth of h1 and a velocity v1, right? If it undergoes a hydraulic jump and the new velocity is v2, calculate the new water depth using the principle of constant discharge. So, principle of constant discharge is small q equals to v1 h1 equals to v2 h2, right? So q will be for 0.4 into 6, that is 2.4 meter square per second. Now h2 will be 2.4 q by v2, that is 1.5. It is becoming as 1.6 meter. Next, a non-finished concrete rectangular channel has an inclination I and a hydraulic mean depth m. Using the Gangulet-Cutter equation, calculate the velocity coefficient c. Assume the roughness constant n. So directly we have to go back to the empirical equation. For empirical equation case, the equation will be given to you. Okay, so you don't need to remember. But the basic equation you need to remember how the equation is coming. Like the expression of critical velocity, like the expression of critical energy, specific energy, critical depth, kind of. Okay. So this is the expression 23 into 1 by n, 23 plus 1 by n plus 0.00155 I by I, sorry. So it is C equals to critical velocity coefficient. It is 23 plus 1 by n plus 0.00155 by I divided by 1 plus 23 plus 0.00155 by I into n by root m. One plus 23 I into yes. So now putting all the values are given. So I'm not writing again the values, just calculate it. So it is I is this. This is top, like numerator is 82.8568 divided by this 1.3729. So now C is coming as 60.348. 60.348. This is just a mathematical calculation. Nothing, you don't need to use your brain. Next. Yeah. So prove that for a constant discharge Q in a rectangular channel, the critical point of minimum energy occurs when the velocity head is exactly half of the water depth. So the derivation is important. So specific energy expression was E equals to H plus Q square by 2GA square, right? So now when the dH, the critical point of minimum energy, means dE dH equals to 0. So if you do the derivation, so it will coming as 1 plus Q square by 2G will be constant. So there will be a square, a to the power minus 2, so this will cancel out, there will be a minus. So it will be GA cube into dA dH, right, equals to 0. Also we know that A equals to B into H. So dA dH will be B, right? So it will be 1 equals to Q square by GA cube into B, right? Also A cube is there, like, right? So Q square B 1 equals to Q square B GB cube H cube. Now what we can think of is, okay, these are defined if you remember. Yeah. So this is coming as 1 equals to Q square by GB square H cube. right? Another thing is there, like V equals to Q by A. We know A is again Q by BH, right? So what can be written? So Q by BH, so V square can be written as Q square by B square H square, right? So if we substitute this value in here, separating, so it was 1 equals to Q square by G B square H cube. So it is 1 equals to Q square by G B square H cube. So if we differentiate it like 1 by GH, it will be Q square by B square H square, 1 equals to, which is nothing but 1 by GH equals to V square. We have just seen that. Okay. So what is coming? So now V square is coming as GH, right? So V square by 2G will be H by 2. So what was the expression? So it is said that the velocity head is exactly the half of the water depth. We have found it, right? These derivations are important to do by your own. Okay, do it. Next question. A 5-meter wide rectangular channel is designed to operate at its critical specific energy. In the total energy, the channel bottom EC is what is the total discharge? Right, so EC is given. So that means HC we can calculate. So EC is 1.5 of HC. So HC will be 2.4 by 1.5 equals to 1.6 meter. Now we can calculate. We have calculated this earlier also. So there is an expression like Q square equals to HC cube G. So it is coming as 40.18 and Q is coming as 6.34 almost. So 6.338 meters square per second. Now we know, so Q equals to capital Q by B, right? Q is known. So capital Q will be Q into B. So it is 31.7. 31/600, that means almost 7 meter cube per second. This is the answer. Last question for today's session. Water flows in a channel at a depth of 0.8 meter with a velocity of 3.5 meter per second. Calculate the Froude number and determine if a hydraulic jump is likely if the flow is suddenly decelerated. So traveling wave. So this is the traveling wave velocity. So traveling wave velocity we have to calculate as GH. So it will be 9.81 into 0.8 will be 2.81 meter per second. So this is the so Froude number definition is V by Vc, right? It is flow velocity is greater than the traveling velocity. Ratio of this two. I have written the ratio right, I think. Let me check. Flow velocity by traveling velocity, yes. So what it is coming? Flow velocity is given as 3.5 and the traveling velocity I have calculated 2.81. So it is coming 3.5 by 2.81. So it is 1.24. It is 1.24 means greater than 1. So it is a supercritical flow. So it is a basically it is a supercritical flow because Froude number is greater than 1. So it is a supercritical flow because if R is greater than 1 and if the flow is and supercritical flow means that is a rapid flow that will be unstable. So this is likely. Hydraulic jump is likely if decelerated suddenly. Okay. So that's for today's class. I hope you have understood the basic concepts of open channel flow velocity, its maximum uh, size, right? Its maximum size or its maximum dimension, how the discharge and flow velocity can be maximized. You have understood these things and how this is leading to the zone of specific energy and from there it is considering the minimum specific energy and the concept of uh, critical depth, and you know that if the critical depth is lesser than the original depth, then it is a subcritical region, and if it is greater than the original, then it is a supercritical region, and if the flow is suddenly decelerated and it will have some kind of back pressure from supercritical zone to subcritical zone, and that is called the hydraulic jump. And the similar concept if it is happening in a compressed gas, that would be subsonic flow, supersonic flow, and a shock wave respectively. I hope you have understood. If you have any clarification, you can again go through the lectures. I will be uploading this lecture by tonight, and please do the derivations by your own because it will be very important, and please solve the problems also. Okay, we'll meet you on next week. So till then, goodbye. Thank you.